The Concorde's maiden flight in 1969 marked a breakthrough in aviation, slashing transatlantic travel time to mere hours. Yet, supersonic travel soon proved impractical due to massive costs and deafening sonic booms, restricting flights over populated areas. After 30 years, the Concorde was retired. Now, NASA and Lockheed Martin aim to bring back supersonic travel with the X-59 QueSST, designed for near-silent flight. But how do they plan to succeed where past attempts failed? Supersonic aviation began with the Bell X-1, piloted by Chuck Yeager, proving speeds beyond Mach 1 were possible. The Soviet-built Tu-144 then became the first commercial supersonic jet in 1968, narrowly beating the Concorde. By 1969, it was also the first passenger plane to exceed Mach 2. Though visually similar to the Concorde, the Tu-144 suffered from poor engineering, excessive noise, and an uncomfortable cabin. Forced to rely on afterburners, it was retired after just 55 flights. Meanwhile, the Concorde endured until 2003 but ultimately couldn't overcome its challenges. Despite its prestige, the Concorde was born from an unlikely British-French partnership, proving that innovation alone isn't enough to sustain supersonic travel. Will the X-59 finally succeed where its predecessors fell short? In the 1960s, Britain's BAC and France's Sud Aviation were separately developing supersonic aircraft but faced challenges. France lacked engine expertise, while Britain had the right technology. A joint effort seemed promising but led to conflicts. A French engineer suggested a moving map display for the cockpit, but the British rejected it, arguing Concorde was a commercial airliner, not a reconnaissance plane. Testing was also problematic. The British flight simulator was subpar, forcing pilots to train on actual aircraft, costly in time and resources. Concorde's high fuel consumption drove up ticket prices, and the FAA's 1973 ban on supersonic flights over cities limited routes. The rise of fuel-efficient aircraft like the Boeing 777 and Airbus A340 further reduced its viability. Ultimately, Concorde's downfall wasn't just technical or economic. The 2000 Paris crash, though isolated, shattered public confidence in supersonic travel. The accident was triggered by a piece of metal on the runway. A piece of debris on the runway punctured a tire, causing a blowout and setting off a catastrophic chain of events. Despite safety improvements, the haunting image of the accident lingered, ultimately leading to the Concorde's retirement. This marked the end of commercial supersonic aviation, and enthusiasm for developing new civilian supersonic aircraft gradually faded. Today, the Concorde is displayed in aviation museums worldwide, a testament to the golden era of supersonic travel. But the story doesn't end there. While the aircraft is grounded, the phenomenon of the sonic boom, caused when an aircraft breaks the sound barrier, continues to intrigue scientists. Similar to a thunderclap, this explosive noise can crack windows or damage structures if left unchecked. It occurs when an aircraft surpasses Mach 1, about 767 miles per hour at sea level, generating compressed airwaves that merge into a powerful shock wave. The intensity of this shock depends on the aircraft's weight, size, altitude, and speed. The affected area, or boom carpet, can stretch up to 70 miles. Since the 1950s, engineers have sought ways to control it, testing various fuselage shapes and wing designs. One of the most effective solutions, proposed by Robert T. Jones and Harold W. Carlson, involves reshaping the aircraft to break up the shock wave, reducing noise levels. NASA took this concept further, experimenting with the quiet spike, an extendable probe on the aircraft's nose, to lessen shock intensity. The biggest breakthrough, however, is the X-59 QueSST, an experimental jet designed to lower the sonic boom to the sound of a closing car door. Developed by Lockheed Martin's secretive Skunk Works division, with NASA's backing through the Low Boom Flight Demonstrator Project. This aircraft aims to revive commercial supersonic travel. The X-59 isn't a prototype for commercial airliners and won't carry passengers. Its real breakthrough is quiet supersonic tech, expected to shape future aircraft worldwide. The QueSST project began with a Lockheed contract in 2016. No one foresaw a global pandemic delaying its first flight, but engineers didn't sit idle. In early 2017, they tested a 9% scale model in wind tunnels at Mach 0.3 to 1.6, paving the way for a summer evaluation. NASA deepened its commitment in 2018 with a $247.5 million contract, officially naming it the X-59 QueSST. That fall, Langley Research Center tested an 8% scale model at extreme angles of attack, improving design refinements. Construction of the X-59 stability and control systems started in mid-2019, though by late 2020, only half was complete. By November 2022, NASA had installed the General Electric F414D-100 engine at Skunk Works in Palmdale, California, generating 22,000 pounds of thrust. It propels the X-59 to Mach 1.5, 990 miles per hour, with a cruising speed of Mach 1.42, 940 miles per hour, at 55,000 feet. While not as fast as the Concorde, which hit Mach 2 at 60,000 feet, the X-59 is far more efficient. The Concorde burned about 6,760 gallons of fuel per hour, while the X-59 is designed to use just 1,190 gallons, thanks to its advanced aerodynamics and modern engine. The result of NASA and Lockheed Martin's massive effort is an aircraft nearly 100 feet long, with an elongated nose making up a significant portion of its structure, a 29.5-foot wingspan, and a maximum takeoff weight of 32,300 pounds. The X-59 stands apart from any aircraft before it. Traditional aircraft generate shock waves as they approach transonic speeds, leading to a loud sonic boom. However, the X-59's sleek, narrow fuselage, sharp nose, and compact wings are specifically designed to prevent these shock waves from merging, drastically reducing noise levels. The aircraft's design follows a theoretical foundation that emphasizes its slim, high-aspect ratio fuselage. Nearly a third of its length is concentrated in its elongated nose, which plays a crucial role in absorbing and managing shock waves during flight. Unlike conventional jets, the X-59 features a cockpit without a protruding canopy, housed toward the rear of the fuselage. The aircraft is powered by a General Electric F414 engine and incorporates a small forward horizontal stabilizer, a mid-mounted delta wing, a conventional vertical stabilizer, and an additional horizontal stabilizer on top. Every aspect of its structure is meticulously crafted to minimize shock wave formation. Inside the single-seat cockpit, the control panel consists of 4 screens of varying sizes. 3 display different types of flight data, while the 4th serves as both a windshield and a heads-up display. To keep costs down, the X-59 heavily relies on readily available components from existing aircraft. Much of its cockpit comes from the T-38 training jet, its landing gear is sourced from the F-16 fighter, and its F-414 engine is borrowed from the carrier-based F-18 aircraft. Unlike traditional supersonic jets, which produce an explosive sonic boom, the X-59 generates only a series of soft thumps when breaking the sound barrier. NASA and Lockheed Martin aim to reduce its noise output to just 75 decibels, comparable to a car door closing, whereas the Concorde reached 110 decibels. In typical flight conditions, the X-59's noise level could be as low as 60 decibels, similar to a regular conversation. As an experimental aircraft, cost efficiency played a key role in its development. Many of its parts, including the landing gear from the F-16 and the cockpit canopy from the Northrop T-38 Talon, were repurposed from other aircraft. The engine system integrates elements from the Lockheed U-2 Dragon Lady and the F-117 Nighthawk, while the control stick comes from an older Lockheed aircraft. Only about 10% of the X-59 consists of entirely new components, earning it the nickname Frankenplane. Despite this, Lockheed Martin utilized cutting-edge manufacturing techniques, making the X-59 the first Skunk Works project to employ highly precise automated drilling and assembly methods. One of the aircraft's most unconventional features is its lack of a forward-facing window. Instead, the X-59 relies on an advanced external camera system to assist the pilot with navigation. The External Vision System, XVS, provides a clear forward view using a high-resolution camera, supported by the Collins EVS-36 multispectral imaging system mounted beneath the nose, which enhances visibility during landing. Could the X-59 pave the way for a new era of civilian supersonic travel? Only time will tell.